In section 4.1, we're going to decode the information contained in chemical equations so we can successfully use them, write them, and balance them. The book's learning goals covered our one learning outcome, so let's begin. Reactants rearrange their bonds to form products. For example, two hydrogen molecules react with one oxygen molecule to form two molecules of water. Chemical formulas tell you what happens during the reaction. Coefficients tell you in what proportions the reaction occurs. Let's look at another example. Information in parentheses tells you the physical states of the reactants and products. Solid, S, liquid, L, gas, G, and aqueous solution, AQ. Reading this equation from left to right tells us that 1 mole of aqueous magnesium iodide, MgI2AQ, reacts with 2 moles of aqueous silver nitrate, AgNO3AQ, to produce 2 moles of solid silver iodide, AgIS, and 1 mole of aqueous magnesium nitrate, MgNO3 aqueous. Do you see how compactly this chemical formula tells us all the information written out below? By the way, if you want to see this reaction, it's in figure 4.2 of the textbook. Some reactions require special conditions to move to products. These reaction conditions are sometimes written above or below the arrow. For example, heat is needed to cause magnesium carbonate to decompose into solid magnesium oxide and carbon dioxide gas. It can be written out as the word heat, or sometimes a delta sign will be used instead. Table 4.1 summarizes what we just covered. Take a minute to review and jot down some notes if needed. When writing chemical equations, we must obey the law of conservation of mass, meaning that the same number of atoms of each element that appear on the reactant side must also be noted on the product side. We accomplish this by balancing the reaction. In the top reaction, we have 1 mole SO2 and 1 mole O2 reacting to produce 1 mole of SO3. Counting the atoms, we see this represents 1 sulfur atom and 4 oxygen atoms on the reactant side, but the product side only shows 1 sulfur atom and 3 oxygen atoms. We can balance this reaction by playing around with the coefficients, the numbers in front of the compounds, to balance the atoms on both sides. This brings us to the most important principle that must be observed when balancing chemical equations. You can change the coefficients, the big numbers in front of the formulas, but you must never change the subscripts in the formulas because that changes the identity of the compounds. Let's look at some other helpful guidelines. If a polyatomic ion shows up exactly the same on both sides of the reaction arrow, balance it as the polyatomic ion and not as separate atoms. If an element shows up in only one reactant and one product, it will save you some time and effort to balance that element first. Next, balance any remaining elements. I'll show you a handy accounting trick for doing this, since you may have to change some coefficients a few times to get it right. Finally, you'll verify that the number of each type of atom is the same for the reactants and the products. Sometimes you'll accidentally overshoot the lowest whole number ratio that will balance an equation. If that happens, divide all the coefficients by the greatest common factor. If you have a fractional coefficient, which is less likely, you'll want to clear the fraction by multiplying all coefficients by the denominator in the fraction. Let's put these guidelines to use. Let's balance this equation showing the reaction of barium hydroxide and hydrobromic acid to form barium bromide and water. First, we look for polyatomic ions that show up the same on both sides. We don't see any, so let's write a list of elements under the reaction arrow and take stock. We have 1 barium atom, 2 oxygen atoms, 3 hydrogen atoms, and 1 bromide atom on the reactant side. On the product side, we have 1 barium atom, 2 bromine atoms, 2 hydrogen atoms, and 1 oxygen atom. Next, we'll balance the atoms that show up in one product and one reactant, which is everything except for hydrogen. Barium is balanced. Adding a coefficient 2 to water on the product side balances oxygen, but takes the hydrogen on the product side from 2 to 4. If we add a coefficient 2 to HBr on the reactant side, we see that the equation becomes balanced with this final adjustment. Reviewing our work, we see that the coefficients are the lowest whole number ratios and the equation is balanced. So our job here is done. Try this one on your own. Remember to balance polyatomic ions if they are present on both sides. Then move on to elements that appear in only one reactant and product before balancing the remaining elements. Here's a challenge question. Please do not Google the answers. This is a good chance to practice concepts learned earlier in the course. Write the balanced equation for the reaction of sodium hydroxide with phosphoric acid to produce sodium hydrogen phosphate, Na2HPO4, and water. Sodium hydroxide is NaOH and phosphoric acid is H3PO4, giving us the unbalanced equation NaOH plus H3PO4 yields Na2HPO4 plus H2O. Next, let's balance the polyatomic ion phosphate since it is present on both sides of the equation. Next, we'll balance elements that appear in only one reactant and product. We'll balance the remaining elements, then verify that we have balanced the equation using the lowest whole number ratios. This is just an introduction to balancing equations. Now, the rest is up to you. Find lots of equations to practice balancing at the end of the chapter, using the activity in Figure 4.5, and even online using trusted sources such as OpenStax Chemistry and Khan Academy, because practice increases your speed, proficiency, and accuracy. As always, I'll leave you with the parting thoughts of the authors. Be sure to let the video finish playing through so that your score transfers to Canvas.